Good afternoon. So I'm going to take you out of your Vietnamese sandwich, which is always a delight. And thank you very much to Andrea Galindo. I've not seen her yet, but the sandwich have arrived. So Andrea is the coordinator of the Center for the Study of Environment and Society. And she is the one who has organized, kind of the lunch today. This lunch is a modest lunch, but it's kind of a modest lunch to bring people to great talks and great speakers. I'm André Draxler. I'm the director of the, we call it CSCS, the Center for the Study of Environment and Society. And I'm delighted this afternoon with CSCS, but also the Shell Center for Sustainability. The director is here, John Anderson. The British Consulate of Houston, and the Baker Institute to host our speaker today, Dr. Julia Slingo. It's a pleasure to have you here. I'm not going to make a long introduction. We are a bit, short on time. Some of the students might have to leave at about 1 o'clock. So Dr. Slingo is currently the chief scientist at MET, the Meteorological Center in UK. And she was the director of climate research at NERC, the National Center for Atmospheric Science. And she's a professor of meteorology at the University of Reading. You might have received a little pamphlet. The title that is on our little advertisement is not the right title, but the title is shorter and more important probably, Met Science and Service to Society. Julia, it's a pleasure to have you here.
Well, thank you very much for that warm welcome. And yes, it is a great honor to actually be standing where so many eminent people have stood, and to have the opportunity to just talk to you briefly about what the Met Office does within the UK and how we relate the science of weather and climate to policy issues. So that I apologize, there's not a lot of hard science in here, because I thought for the sort of discussions that probably we wanted to trigger here today, it was more to give you a sense of the big issues for science and how they are driven by policy needs. Very happy to let you have further information on what we're doing across geophysical hazards in due course, if that's of interest. But see if I can get this to work. Here we go. I just thought I'd say very quickly the role of the Met Office in the UK, because we have a very unique position, I think, in UK science, in that we are the UK's national meteorological service as part of the World Meteorological Organization. We provide the UK's public weather service and national severe weather warning service, but we have played a very dominant role in academic and in atmospheric science in general in the UK science base. So traditionally, if you wanted to do research into atmospheric and climate science in the UK, you went to the Met Office. You didn't go into the university sector. So when I started my career in the early 70s, that tells you how old I am, I went to the Met Office because it was the premier science organisation in the UK and remains so. But I'm very glad that actually, particularly over the last 20 years, atmospheric and climate science has grown substantially in the research and academic community. And part of my role as chief scientist is to form really good partnerships with academia to make sure that we make the most of that really fantastic growth that's happened in the university sector and in the research council centres. So, Met Office, leading science organisation in the UK. We also includes the Hadley Center for Climate Prediction and Research, which is arguably one of the world's leading climate research centres. That was established by Margaret Thatcher when she was Prime Minister in 1990 as a response to the emerging threat of climate change. And that centre is very much directed to providing policy advice on climate change. So although we do cutting-edge research there, all our science, and that's true in the weather research that we do, is geared to providing policy advice to government or warning to UK citizens at home and abroad on impending weather hazards. We're not that large an organisation compared with other major national meteorological services around the world. We have 1,700 staff in total, mostly based at Exeter in the West Country in the UK. But I have under my care as Chief Scientist and Director of Science at the UK 500 scientists working across everything from the absolute fundamentals of atmospheric and ocean science, what we call our foundation science, to climate science, looking at climate change, all sorts of issues of the science that underpins mitigation, adaptation, right back to what's tomorrow's weather going to be like, or even what's the weather going to be like in the next few hours. So my 500 scientists cover everything from very detailed weather forecasting science to long-term climate change science. We are a service organisation, so we have a wide range of bespoke products and services that we offer now across many sectors, and that's also absolutely fascinating. So we don't just do weather and climate science for weather forecasting, we do it in the context of what, say, the energy sector needs, or the water sector, or the farming communities need, a whole range of users, and that's really interesting. So when we look at what we do at the Met Office, we're really increasingly having to serve science needs across the whole of government, and this is just a mishmash of all sorts of government departments at the bottom here that you won't really appreciate, but if you show this in the UK, of course, everybody recognises these things, but you can see everything from we're here with the Foreign and Commonwealth Office for May, but we advise the Foreign Office when there are disasters like the Fukushima disaster. We were working very closely with the Foreign Office about where the fallout from the nuclear reactor was going to be and whether it was necessary to evacuate British citizens from Japan. And in fact, we felt it wasn't necessary, and we were right. To all sorts of Department of Health, right across the other administrations, Department for Transport, so it goes on. So I as Chief Scientist work very closely with the Chief Scientific Advisors across all the government departments to ensure that they have access to the best weather and climate advice, particularly when there are emergencies. And we were talking this morning about the Icelandic volcano going off nearly 2 years now, but closing down the whole of UK airspace and beyond. And it was, I was spending a lot of time in Whitehall trying to make sure that the ministers and the aviation authority and so forth had the best possible advice from us. So you can see here all sorts of things. You probably can't read them, but everything from migration and global environmental change, food security, natural hazards and infrastructure. We now have a space weather prediction service through a very nice collaboration with NOAA. Here we do stuff on blue tongue, animal diseases, everything from natural sudden disasters. There's a big fire up there when an oil refinery blew up in near London, to massive flooding and drought and so forth. So huge range of policy advice that relates to weather and climate, but we need to couch in terms of what those users want. So a lot of interpretation, expert judgment goes into the advice we give. We're also unique in the sense that we have weather forecasting and climate prediction in the same organisation, and that is not often found. And we base all that on the same modelling system, the unified model. And the unified model itself is unique in the way that it's been formulated, so it can be employed across the whole breadth of space scales from a few hundred meters to 100 kilometers and beyond. And I don't think there's any other weather climate model that has that capability in the way that we've formulated the dynamics of the model. I won't go into the details of that, but it offers us a fantastic opportunity to look at multi-scale problems, and it gives us a fantastic opportunity to exploit what we now call this seamless approach to the science modelling and prediction of weather and climate. Because that's actually, climate is nothing more than the statistics of weather. When people talk about climate impacts, they're mostly talking about the impacts of hazardous weather as the climate varies or changes. So how many hot days do we have? What's the incidence of heavy rain events? Those sorts of things. High winds, all those sorts of things. They're actually interested in the weather. And this is where I think the coming together of weather and climate is so important. The real world doesn't know the difference, and nor should we, really. We shouldn't segregate them. They are one and the same thing. And so what we've done over the last few years is to really produce much more of what we call a seamless forecasting service, where we look at all timescales from hours ahead right out to a century ahead, and think of it as a seamless system. And we think of it also in terms of what are the user requirements. And you can't probably read this from where you are, but there are all sorts of things in here to do with operational planning, resource management, insurance, reinsurance, market trading, regulatory standards, adaptation strategies, through to mitigation policies. And many of these overlap in a huge area of very many timescales. If we look at this, the sweet spot, what we're calling the sweet spot now, which is the month to season to year to decade ahead, or a few decades ahead, where a lot of decision making goes on across many, many sectors, and major decisions made on what sort of infrastructure to invest in to make yourself resilient, prepared for what the weather and climate may throw at you. The other thing that we've done in the Met Office is also, over the years, evolved our weather models to Earth system models. And this, again, puts us in a very strong position in that we started here in the 1970s. This was where I was working in climate modelling. This is still our weather forecast model up here in 2000, but we add to it the other components, particularly those that act on longer timescales, like the oceans, the aerosols, the chemistry, the carbon cycle, and so on and so forth, the ocean carbon cycle, to make a holistic Earth system model. We're very skilled now in the development of holistic Earth system models that look at the key feedbacks and processes that drive short and long-term changes in the Earth system. And that is being used more and more to guide policy making, particularly around mitigation, but also adaptation. It's very interesting that actually I think the policy agenda is changing, and so has our research agenda has had to change too, that the language that we often hear now around UK government is not just mitigation and adaptation. There's a lot of conversations about resilience and preparedness. And that means resilience and preparedness now as well as in the decades to come. And it's quite clear that we as a society are far more vulnerable to hazardous weather and natural climate variability than we were 10, 20, 30 years ago. We live in a globally interdependent society. We depend on global infrastructures for our day-to-day life and our well-being. So something that happens to you in Texas could well have an impact on the UK in terms of all sorts of critical infrastructure, but also critical resources. There are so many examples of this. And as a society, we are becoming more and more vulnerable. And we saw that with the Icelandic volcano recently. We may see it in space weather events. There are all sorts of ways in which we need to be better prepared, more resilient. And so a lot of what we do at the Met Office is actually trying to deliver that, whether it's for the few hours ahead or whether it's looking forward a season ahead, so that we can be more prepared. But also we recognise that actually the next 20 to 30 years we're committed to a certain level of climate change that's absolutely independent of the emissions that we may, what emission mitigation strategies we pursue. What we've already emitted into the atmosphere, the carbon loading of the atmosphere, that is committing us to a level of climate change that we can't avoid in the next 20 to 30 years. And that's really important because people are now beginning to ask very difficult questions of us as scientists. What are the regional and local changes in climate, especially rainfall, going to be like? I mean, are you in Texas going through one of the worst droughts you've had for a very long time? Are you going to see these more frequently or less frequently? Are you going to see more heavy rain events that will, or higher incidence of tropical cyclones that will challenge your infrastructure and the way you protect yourselves? So, and what does all this mean for us as a society and for the natural environment beyond just ourselves and our infrastructure, but ecosystems and all those sorts of things on which we, ecosystem services on which we depend? So this is very challenging. This is actually talking much more at the weather climate science end. It doesn't say anything about, you don't have the uncertainty of emission scenarios, mitigation policies to deal with. And it's very clear that for those of us working in this field, that actually there may be a compounding factor between the natural variability of the climate system. We're in a La Nina at the moment, as you know, and global warming, which may give unprecedented extremes. And we see an increasing number of these as the years go by. The first for us in the UK was the 2003 heat wave, which particularly in France, was much more severe in France, but actually killed 20,000 people and also had devastating impacts on our agricultural production. And we were able to directly show through some very good science that there was a major contribution to that heat wave from global warming. And there's anecdotal evidence and increasingly robust scientific evidence to suggest that we may be seeing more unprecedented extremes as a result of this compounding effect. And that requires us as the Met Office, as scientists, to look at making sure our climate models are actually looking at weather at regional and local scales. And that means increasing the resolution and sophistication of our climate models to bring them in line with our weather forecasting models. And it's becoming a huge computational challenge. You need very large supercomputing resources to do this well. But we have the science there that we can bring forward very rapidly to this, to serve these needs if we can find that computing resource as a community. And this is, again, our government. This is the Adaptation Subcommittee. And I thought this is a nice quote from our Secretary of State for the Environment in just over a year ago, where she says that today's report provides a wake-up call. It recognises that there is no part of our society which is immune from the effects of climate change, which means that every part of our society must think about its resilience. We must, all of us, take steps now to recognise the problem, analyse the risk and plan ahead. There is much more to be done, but the solution is in the hands of us all as businesses, citizens and consumers. And that's very much where we at the Met Office see our role in all of this, that yes, we can provide the underpinning science, but we need to reach out to those who actually can make the difference, whether they're the public, whether they're the politicians in government deciding on policies, or whether they're businesses who need to respond in some way or another. So we have increasingly developed our climate services over the last 3 or 4 years, and we now are playing, I think, internationally a leading role, not only in weather services, but climate services too. And those climate services are not just about adapting to climate change, they're about being resilient, being prepared for climate variability. So could we have predicted with some useful level of confidence the sort of drought that you're now going through? And if that information could have been communicated to you so that you could have done a very detailed risk assessment, could some of the more serious aspects of that drought been avoided? These are very good questions, and very important questions. So we do a lot now with these major sectors in the UK and increasingly internationally, looking at these whole set. These are just a set of I think, the major sectors that we work with at the moment, but there are many more, of course. And I just give one very noddy example, and you won't really be able to see this, but this is the sort of way in which we communicate. In this case, this was the nail network in the UK, and it's about looking at track buckling and track conditions, and how often temperature thresholds are likely to be exceeded, which would damage the railway tracks and mean that you would have to either find a different construction for the tracks to make them more resilient, or you'd certainly have to be prepared to have more maintenance of the tracks and have people going out and about, what heat watchmen they're called, checking that the infrastructure is still safe. And this just, for them, they can look at track buckling, they can look at track maintenance, they can look at heat stress, passenger and freight risk, pluvial flooding through a web interface that takes them from the climate information to what they need to know. And this is just, as I said, an example for track buckling, and this is showing the baseline and then what it would look like in the 2030s. So you can see that in the arteries that would run out from London, which is where a lot of our rail infrastructure is, the risk has substantially increased. So that allows them to put that into their decision making. So that's just one example, nice web-based tool for them to use to look at different scenarios. The Met Office has had a long and illustrious history. We celebrated last August 150 years since the first public weather forecast was made, and this just shows it was made by a man called Admiral Fitzroy up here. The Met Office was founded in the Board of Trade under Fitzroy in 1854, mainly to provide warning to shipping. So it was the shipping forecast that he was supposed to do, but he decided that he was quite good at this, and in 1861 he issued his first public weather forecast, and he published it in the Times, and he made the bad mistake of getting it right. And so that everybody thought, great, this is a whole new thing. He then got the next few wrong, and thereafter he had a very difficult time, and got into some very difficult correspondence through the Times, but not only with readers of the Times, but actually the Royal Society also disclaimed him and said that he was that weather forecasting was non-scientific and they weren't going to have anything to do with it. And here he is saying something very along the lines of what we say today, that they are not dogmatic predictions of what will actually happen. Increasingly, of course, we give probabilistic forecasts, even a few hours ahead. And we have to. We live in a chaotic world. The one flap of a seagull's wings will forever change the course of the weather. Very famous words on chaos from Lorentz in the early 60s. But here's, in fact, in 1963, Lorentz wrote those words. 100 years earlier, there is Robert Fitzroy saying that these are just expressions of probabilities. And if you can't read, this was, to those whose hats have been spoiled by umbrellas having been omitted. So as always, the public was upset because it had upset something about them. But it's continued to be a very political science. And just to go back to poor old Fitzroy, he committed suicide a few years later. not completely because of the ridicule of his science, but also he was captain of the Beagle in the voyages with Darwin. And he was, as a very religious man, deeply disturbed by Darwin's Origin of Species. So he's a fascinating man. He founded the Met Office, but he also captained the Beagle. But we continue to be a very political science, and here is what is now, of course, very political, what is happening to the weather, to the state of our climate system, and a lot of debate, which again challenges us as scientists. We need to be able to explain some things. So here is the 2011. These are ranked temperature anomalies, so the colours give you the different decades and so forth, going back to 1850 in the top colour here. So you can see all the clustering of the warmest years being in the last 2 decades. 2011 is actually right down here because it's a major La Nina, and we know that enso cycles have a big impact on global mean temperatures. And if we go back, here's 2010, quite a lot warmer. It was the second warmest year on record. The warmest year was 1998, but it was a massive El Nino. And lots of people say, well, global warming stopped 1990. Ever since 1998, it's been cooling down. And they forget to show that 1999 was way down here a year later. So the impact of El Nino, La Nina cycles is about 0.2 K year to year. But you must always look at the long-term trend. It was ever political. If you look further down that record, you find 2 purple bars, 1877 and 1878, sitting amongst a cluster of years 100 years later. So what are those 2 doing down there? Well, they were that was probably the strongest El Nino that we've ever seen in terms of the record. And as ever, it had very political ramifications. This was at the height of the British Empire, and a huge presence in India. So our economy, 1/5 of our GDP, depended on India and Indian cotton and so forth. And the Indian economy itself, was single-mindedly, as it says, focused on its grain harvest. This huge El Nino led to the Great Famine of 1877 and 78, an enormous pressure on the British Empire, an enormous problem of governing India, and a huge impact on the dividends paid to investors in the UK. And here's Queen Victoria on her throne, disputed empire, with the starving millions saying, well, what's the empire doing for us? And out of this was born seasonal forecasting. So Henry Blandford, who was then the head of the Indian Met Department, started the whole process of, he called it seasonal foreshadowing. But it was the birth of seasonal forecasting because the scientists at that time thought that control of famine through climate prediction would mean that India could be governed more effectively. They, of course, found it incredibly difficult to do. But it's always been a political science. It's fascinating science because it is in that political arena, and we play so close to policy, and policy is so close to the bleeding edge of the science. But what we in the Met Office has learned over the last few years, that actually it's not just weather and climate science that matters, it's the way that it interacts with so many other parts of the geophysical system. So we may be a driver of hazards, weather and climate may be a driver of hazards or even a mediator of hazards. But you often, if you want to look at, really do well in dealing with, as I said, this interdependent environment, we need to look across so many disciplines. And I've had a fantastic week talking to the hydrologists in Texas and how our science can meet their science so we can do a more effective job on managing flood, drought, waterborne pollutants, etc., wildfires, and so on and so forth. This is just a few examples of where our science meets other sciences, and we really need to do this to make it work. And so in the UK, the Met Office has now been pioneering something called the Natural Hazards Partnership, which has the blessing of the UK government, our Cabinet Office, drawing together both the service community but also the science community, the research community, to really actually do proper natural hazard warning services, management of natural hazards, end to end from the raw basic science through to what the user requires to make their decision. Very exciting development. It began with our flood forecasting centre, and now we're reaching out to many, many other parts of science and the user community. So that was just to give you a sense of how Met Office science works through to policy and the sort of issues that we now have to think about, and the way that weather and climate science is very political, but it's my role as chief scientist to make sure that what I provide to policymakers is the best, the most honest, the highest integrity, the science advice that they need to underpin their decision making. So thank you for listening, and I'm happy to have some questions.
Thank you very much, Dr. Slingo. For the question, because this is being webcast, you need to approach the microphones. So the floor is open to questions. So, but please kind of come to the microphone before you ask it. Thank you.
Thank you, Doctor. And if it's any consolation, I began my career in the 1970s as well.
Okay.
I am involved in the rice industry, agriculture around the world, and one of the issues is water, whether it be a surplus or drought. Any thoughts for, as we look forward to dealing with the shortage or the surplus of water around the globe?
I think you're absolutely right that when we think about our climate variability, climate change issues, it all comes down to water in the end, about too much, too little at the right time in the right place. And that's been a very, very big challenge for us as weather and climate prediction people, because this is one of the areas that's most difficult for us to do. So actually in my science strategy at the Met Office, one of the I have 4 planks to my science strategy. One of them is the water cycle and quantitative precipitation forecasting. The word quantitative being very important. And I think before we can even answer your question, we have to be able to break the back of this, being able to predict what will happen to the water cycle, what will happen to rainfall, not just the seasonal mean, but also the frequency intensity statistics. Many agricultural systems are hugely sensitive, not to the mean, but to how it comes and when it comes. And that means pushing our model resolutions higher and higher, and I talked about that earlier, about being able to resolve weather systems, being able to resolve rain-bearing systems. And we're almost at that point when we can really break into that, and I think that will revolutionize actually the way in which we can then integrate what comes out of the sky and what it means for how we manage water, whether it's for agriculture, whether it's for human use, what sort of the quality of the water and so forth, and therefore how you manage, particularly in areas where there's a shortage of water, how you manage the different demands on water. And we have to, I think, very clearly also, I didn't show it, but I think we have to look at water security and food security together. They're the same. They're intimately linked, and when we look at our Earth system modelling as we go forward, we're incorporating irrigation planning, we're incorporating crop models in our Earth system models so that we can get this fully integrated view of water and food together.
Yeah, very much so. And I assume that will be published when the predictive modelling are available?
Absolutely, yes. And we're already doing quite a lot of work in this area, actually, through the Department for International Development in Africa and places like that. So again, if you want to find out more about what we're doing and what the potential is, do contact me.
Okay, great. Thank you very much.
Thanks a lot for taking the time to chat with us. Just a quick question. Given that a lot of countries are sort of embracing, austerity measures, budget cuts, do you see that negatively affecting both the research budget as well as what steps countries do take to kind of try to address climate change? And sort of follow up on that is, what would be sort of like the ideal policies that you would look and sort of advise policymakers to take?
Right, so lots of bits in this question, I think. Yes, for sure. I mean, the economic situation is very challenging, and I think what we've seen certainly is that in a way it's almost climate change has gone off the agenda because of that, and not surprisingly, really. But I mean, for the UK, and I know the science base has been in some cases quite hit quite hard in the US. In the UK, science has been very strongly defended by our government, and I mean, the Met Office, we haven't really been affected by the economic situation because this is seen as so important to government policy. And there are other examples I could have shown you where, we're at the heart of so much of the decision-making that goes on, that they see the investment in the Met Office as a small price to pay for the sorts of costs that climate and weather impacts can have on the country. And even in our research councils and universities, I think we're, a colleague here, senior member of our academic community, I think we're weathering it reasonably well at the moment. So that's good. What was the next bit of your question?
Sort of like, what would be the perfect ideal policies that you would try to advocate for, or you would sort of advise policymakers to look at?
I'm not going to answer your question, because actually I'm the chief scientist of the Met Office, and my role is never to give policy advice. I could have my own personal views, which I'm not going to share with you. But I have to make sure that, as chief scientist, what I do is make sure that we provide an authoritative voice to government on the science, that they get the best possible advice on which for them to make the decisions around policy, because they're the experts and I'm not. I do the bit that I do well, and that's our role in the Met Office, that we have to stay true absolutely to the science and just the service that we provide on weather and climate forecasting. So I'm sorry, I'm not going to answer your question.
Yeah, thanks a lot.
Over the last few months, there have been preliminary reports from the Russian Academy of methane releases out of the Arctic.
Yes.
I'm curious as to what your community of scientists and yourself are thinking about this and your reactions to it.
Yes, we've been following this, of course, and this is one of these known unknowns, if you like, for climate change. I think they're quite alarming in the sense of what is happening around the rim of the Arctic Ocean, and those are very important measurements that are being made. And we are actually, of course, actively including now into our Earth system models the whole business of melting permafrost methane releases, looking at worst-case scenarios for those sorts of those potential changes that could go on, as particularly the northern latitudes warm, and you start to beginning to release both methane hydrates, but also from the land, from the melting permafrost. Very alarming. Great interest to us.
Antonio, it's Espinosa, and I am a farmer in Paraguay, South America.
Right.
And but my question is related to an article that was in the Wall Street Journal a couple of weeks ago.
Mm-hmm.
And the gist of the article was that in the last million years, only 10% of that time has the climate been warmer than it is now. And it went on to point out that we would be already past the peak in this particular interglacial period. And so my question goes, there are two questions that arise. The first is, in your view, how accurate is it possible to determine what the global temperatures have been in the last million years? How accurate or how possible is it to be able to say with any accuracy that it is now warmer than only 10% of the time in the last million years? And the second question is, what is your view of the trend in this interglacial period? What would be the effect if it were not for greenhouse gases and the global warming phenomenon?
Right. So, of course, there are uncertainties in measures of global temperature as we go using paleo proxies, which is what have to be used to reconstruct the past million years. But the fact of the matter is that levels of carbon dioxide are now much higher, 50% higher or more than they've been in all that period. And so we know that, and we know that even within the bounds of uncertainty, we seem to be getting above what was previously recorded in terms of temperature. But that's still, I think, there's still some uncertainties there. I think the thing that worries me most of all as a climate scientist is not the absolute temperature, but is the rapidity of change. So when you look at the past record, yes, there have been fluctuations through glacial interglacial cycles, and we can look at how rapid those changes are, but the way in which our temperature is changing now and is likely to change over the next 100 years is far more rapid, probably 10 times as rapid as anything that we observe in the past. And that has real implications for the ability of the Earth system, that's both the physical system and the biological system, to adjust. And I think that's the thing that we should also be concerned about. What was the second half of your question?
Well, what is your view of these long-term cycles and how they will impact climate forecasting?
Well, we don't, I don't think the expectation is that we're looking of orders of thousands of years rather than hundreds of years to go into another glacial. We're not talking about anything that will save us in the next 200 or 300 years. I think that's a very key point. And the other point around all this is that we also know that what we're doing now will commit us to climate change, not even if we manage to get our emissions under control and the CO2 concentrations under control. There's a long-term commitment for several hundred years from what we've already put into the atmosphere, and also that the state that the system will return to will not be the same as the one when we started all of this a couple of hundred years ago. So that also, I think, is kind of something that concerns me, that we understand the irreversible nature of what we're doing to the climate system.
Thank you very much.
My question is, do you have any joint programs with the Town and Country Planning Department? And if you do, maybe you can share with us some of the work you're doing with them. And the other part of the question is, you presented to us some of the wonderful efforts you're doing in climate adaptation and resilience.
Yes.
And so the other part to this question is, have you also identified climate mitigation as a separate research stream?
Sorry, the last part?
Have you also identified climate mitigation as a separate research stream under your various departments?
Yeah. So we work very closely with the local governments, so the town and count planning people, and we particularly on the weather side, but increasingly on the sort of urban design and and those sorts of things, and the types of buildings we'll need going forward. That's something that we have a very good dialogue with, and so, and again, often through our academic partners as well. We have a very strong programme in the Hadley Center, which is part of the Met Office, on climate mitigation policies, because we're largely that bit of the programme is largely funded by the Department for Energy and Climate Change in the UK. And there are still some very big issues about mitigation policies. So it's not all about CO2. There are also a lot of other species that are co-emitted. Land use change is another part of the whole thing, that you have to look at it in a holistic sense. So sometimes there are a lot of short-lived species now that we understand have quite a big climate forcing on the system, but act on much shorter timescales and smaller space scales than carbon dioxide. And so we do a lot of work, a lot of our work with our Earth system modelling is looking at what do mitigation policies actually mean for the complete Earth system on a whole range of timescales. And that can have very profound implications for the sort of policies you decide to pursue. So yes, we do a lot in that area.
Thank you.
Really appreciate the idea, certainly, of regional predictions, because that will help farmers in their particular country. At the same time, the BBC a couple months ago criticized one of your reports for saying that in Egypt, the flooding probability may go up by 200% or down by 100%, or in Peru that climate change will essentially have no effect on water, when in fact we know there's a big concern about glaciers melting. So it seems like either you're putting out some predictions are either useless, because you don't know if it's going up and down, or even highly misleading. And I was wondering, is there real pressure to, political pressure to try to get out regional reports that may not be accurate or misleading?
Well, what you're referring to, I think, was a set of reports that we did for Durban. And those were done collaboratively with the countries involved. So that information was exchanged with the various countries. It was the first attempt to regionalise climate change impacts. I think my view is that it's really important that we actually put some meat on the bones of this 2 degrees C target. And we work a lot with the Foreign Office, actually, in this area of producing more in-depth studies. The fact of the matter is that the state of the modelling is not yet up to really, really detailed projections that actually can feed through to what farmers want. So this was a first attempt, and I think it was very clear in the report that it was a first attempt. We have the projects ongoing, actually, way beyond Durban, to try and get much more reliable information into there. And the BBC, of course, were cherry-picking nice bits out of the report. Probably out of context, I would advise. The report itself was hundreds of pages long, and each country was tens of pages, sometimes 100 pages long. One of the things that we were here this week in Texas talking about was how we can actually revolutionize the way we look at climate impacts by drawing on our expertise in weather forecasting, where we run our global models, say it's something like 25 kilometres resolution, and then nest down to around about 1.5 kilometres over the UK. And we have the science capability and now potentially the computational capacity to actually do the regional modelling at something like 1 kilometre. And if you think about that, that will revolutionise the way we can interact with agricultural sectors, with water resource managers. And we really need to do that, because the sort of things you're commenting on are now the sorts of things that are coming up, the policy and agendas, and the science and the modelling is not there yet to answer them.
Yeah, thank you. Very important project, but I'm just worried the farmers may be confused in these initial reports.
Absolutely. They should probably make sure they see them in the context, because they were written very much as a first attempt at trying to get something at least on some of these big issues.
Thank you.
So I have a question about collaboration between different governments. Climate change is a very global issue, and I was wondering if you could talk about the communication and kind of isolation between science and politics of different nations.
Well, again, it's not for me to comment on the politics. I think the science collaboration is incredibly rich, and actually what I've, in my career as a meteorologist, I suppose, fundamentally, it's probably unique in the sense that of being an international science where we are always happy to exchange information and to help each other, because we live in a single atmosphere, and you know, the weather I get in the UK probably started over Texas at some point. So, so I think in terms of international collaboration on the science, I think it's fantastic, and you know, I've had some great experiences in the US through collaboration, and we increasingly, as the Met Office, have helped many countries now build up their weather forecasting services and their climate change work and their climate services and so forth, and that's something we feel is very important that we can do internationally. I'm not going to comment on the politics of it all, because it's very complex and it's not for me to say. Thank you.
In your remarks about pushing to higher temporal and spatial resolution in the modeling,
yes.
And also in connecting weather forecasting with climate, a number of interesting technical questions, but let me just ask about one of them, and that is, you have emphasized the expansion of computing capability, but that's only one side of the question. Right? The other side, which is somewhat more difficult, I think, is data gathering. Yes. So that you have a set of initial conditions that's appropriate to the temporal and spatial resolution that you're trying to compute, and that either as initial conditions or as updating the conditions as you move forward. Could you comment on whether those two sides of the problem are keeping pace with one another?
That's a really, really important question, and I mean, it's part of my role as chief scientist is to make sure that the observational base is commensurate with the modelling and the predictions. And in terms of the atmosphere, we have a very comprehensive observational base in the sense that we have Earth observation, and we simulate vast amounts of data into our weather forecasting models. Every 6 hours we make a simulation forecast cycle. And you can actually work out how much the improvement in weather forecasting has come from the observations and from the model. And actually it's a mix of both. So you need a good model to assimilate these observations that are often very heterogeneous in space and time. So that's for the atmosphere. The ocean, which is a critical component of extended range forecasting, so out beyond a week or two ahead, you need to include an interactive ocean. And for climate change, of course, and climate prediction, absolutely essential. We're not in such a good state. And there, I think, you know, the Argo float programs have revolutionized things for us. But, you know, the ocean will always need in situ observations. We'll not be able to sort of get round. With the atmosphere, we've had a huge advantage by being able to observe the atmosphere in a lot of detail from space, because you can see through it, but the ocean is going to be a whole different ballgame. So that's one of my major concerns, is that the more complex bits of the Earth system, as we go into this Earth system modelling, is, first of all, how do you initialise the predictions, but as important, how do you evaluate your models that they're doing something sensible?
Thanks.
Well, it's about 1 o'clock, so we will have not to close. But I have a quick question. How is the Met, involved in this wonderful event that is going to happen in London in 6 months, in terms of weather, or even in some, how the Met was involved in terms of the design, of the infrastructure and so on?
Right. So this is the next Olympics, yes. With great trepidation we're approaching that. So we weren't actually greatly involved. The Olympics organising committee do their own thing, but we have the contract from the Olympic Committee to provide the weather forecasting for the Olympics, both in London and the other venues. And that's meant a major upgrade for some of the forecasting that we currently do, particularly the very high resolution, the 1 kilometre forecasting, air quality issues, all sorts of things. And I'm getting a run through now of quite a few people from departments like the Home Office, wondering if we can say anything that will help them manage the flow of travellers through Heathrow Airport so they don't have immigration queues where people wait for hours and hours to get through immigration because the planes haven't been able to land on time. I can see this ramping up very fast, and most of our staff have been told they can't go on holiday during the Olympics, so we'll be in the thick of it, for sure.
So you do, yes. All
yes.
Right. Well, thank you very much, Dr. Slingo, and it was a pleasure not to host here under this wonderful kind of lights and beautiful buildings of the Baker Institute. We thank you very much the Baker Institute to host kind of this event with us, and have a great weekend, and we will see you at the next event. Thank you very much.